been a while since I've done one of these long form YouTube videos, but we're back at it. So lately on my website, I've been unleashing a ton of content on engineering. So we're doing mechanical engineering right now, a breakdown of a bunch of classes. So we're gonna have strength of materials, we're gonna have thermodynamics, we're gonna have all that good stuff. So I plan to make my website a really good resource for engineers and really trying to bridge that gap between engineering and the industry and academics as a whole. So check it out. You're not going to want to miss this. So, all right. So we're starting with stress in engineering. So what stress is basically a physical quantity that describes a force over a unit area. So when we're doing things like designing mechanical systems, we're going to be um, making sure that these systems are capable of handling stress. It's our job and duties as engineers to be able to make sure that they output and can handle specific stresses and can handle basically their specific operating conditions. Formula for stress, we're going to see that stress is a force over an area. This is probably the most fundamental uh, formula that you're going to see, and a really simple application of stress is going to be this. We're just going to be pulling load upon a bar or a beam. So we have a cross section A, we're pulling with a load P, and bingo, we have sigma equals P over A. So this equation is going to be really fundamental in the industry. We use in America we use units PSI, KSI, and then we like to use pounds. We use kips because we're dealing with a lot of load in high performance applications. And then on top of stress, we're going to have so many different forms of stress. So we're going to have different forms of stress such as normal stress, shear stress, planar stress, principal stresses, compressive stresses, and tensile stresses. So an easy way to look at normal stress, we're going to break into each of these different types of stresses, but normal stress is going to be um, taking basically the stress normal to the normal axis of a component. So for instance, like say we're going to take a plane on this bar here. Uh, X prime right here would be the normal axis, if you will, the orthogonal axis based on this reference plane. So that's what you can designate as normal stress. Compressive stresses and tensile stresses. So we're going to be doing a lot of compression or tension in mechanical systems. So a really easy way to represent it is tension, jaw or feed body diagram. We're going to have arrows pointing away from the system, and then compression would be arrows toward the system. And it's really important that you keep consistent with your signs, your reference designators. So if a unit's going to be positive or negative, that's going to be the direction of one force or another. And then we're going to have beam bending in the industry. So beam bending, super common phenomenon in the industry. We're going to have uh, the equation sigma equals my over y. This is just the moment, the distance from the centroid to the point we're taking the moment of divided by the moment of inertia. So let's say for the beam, it's going to be like base times height cubed over 12 or something like that. So we can take this formula, and this will give us basically the bending moment of a beam, the stress of a bending moment of a beam. And in the industry, we're going to compare this stress to what our allowable is, and we're going to do a bunch of calculations, and we're just going to make sure that our system is going to pass the analysis. And then shear stress is just going to be the stresses represented on an object's shear plane. So let's take this cube, we're going to cut it up, and if we have it as shown, the shear stress represent basically these stresses right here in the red arrow. So relative to the normal axis, the shear stress is going to be, and then for beam deflection, we can use overall. This doesn't cover all cases, but this is just going to be one of the general forms of shear stress on a beam. All right, and principal stresses are going to represent the maximum or minimum stresses subject to a body. So when we're doing stress analysis, we're going to be using a bunch of either FEA software, or we might even use hand calc methods if we want to do something quick and dirty to make sure that everything's good. The thicknesses that we've selected for a certain part are good, or the geometry that we're using for a certain system is good. So this is going to be uh, the equation that basically the software will be computing. This is probably the most important stresses that you're going to see analysis report, and you're going to compare these to what your allowables are and how much margin you have based on stresses uh, that the system is undergoing, versus how much you can handle. And then we have a couple example problems here. So let's say we take this beam deflection problem. We want to determine what the internal forces are at F, given the point at C. Draw a free body diagram. We're going to cut through the cross section and basically write our equilibrium equations as shown. So I'm not going to go too in detail into this. This is just kind of a high level overview of what type of problems you're going to see. And I'm just trying to bridge together what it is between theory and application. So another one's a pressure vessel problem. So if you're going to work in an industry like, say, oil and gas, you're going to want to make sure that the thicknesses or what you're selecting is going to be capable of withstanding operating conditions. So one thing to note is that you don't want to make parts too thick, because then it's going to get pricey. It's going to be hard to manufacture, and then if it's too thin, it's just going to bust. So you're going to want to do best of both worlds, and this is what's going to justify your selection. So as an engineer, you're going to make sure that everything you're going to be selecting is justifiable and that everything is just going to work. All right, so if we take this pressure vessel, certain radius, certain wall thickness, internal pressure, we have a compression load of this much, and a torque of this much is subjected to the vessel. We're going to determine what the maximum shear stress and associated normal stress is in the cylindrical wall. So we're going to take a plate, we're going to represent it as such, and then boom, and then we have specific equations that we can use for calculating normal stresses in certain directions for pressure vessels. So this is an equation we can use, and this is what we get. For the x direction, same thing. Sigma y equals sigma theta. We can use this equation, and this is what we get. And then shear stress. So this is a different form of shear stress regarding torsion. So we have torsion times the radius divided by the polar moment of inertia, and we get this much for our shear stress. So we'll compare these with what the allowable stress of the material is, and determine whether the system is good or not. And then here's some pretty common used formulas. We're going to have axial loading, we'll have torsion, we'll have bending, we'll have pressure vessels, spherical pressure vessels. And so that's pretty much it. So just a quick rundown on what stress is in engineering. Hope you find this useful. If you want to check this out more in depth, more in detail, check it out in the link below. And additionally, I do provide career services, so resumes, cover letters, mock interviews, all that good stuff on my website. Just go right here, services, and you'll see all of them here. But that's basically it, and we'll talk to you guys later.